Right now, on the other side of the planet, in one of the most remote and hostile places on Earth, a piece of ice the length of a small country is cracking apart. And the scientists who've spent years watching it happen are using words they don't use lightly. One of the last things holding this glacier back is poised to disintegrate. Not eventually, not decades from now, as early as this year. This is Thwaites Glacier, the glacier the world nicknamed Doomsday. And what researchers just confirmed about it changes the entire timeline for one of the most consequential threats facing coastal cities everywhere. Let's break down exactly what's happening, why it matters so much more than a single ice shelf sounds like it should, and what scientists are actually watching for next. First, let's get straight on what Thwaites Glacier actually is, because the nickname tends to overshadow the science. And the science alone is dramatic enough without any embellishment. Thwaites sits in West Antarctica, and it's not just large, it's the widest glacier on Earth, stretching roughly 80 miles across, an expanse of ice comparable in size to the entire state of Florida. But its size isn't actually the reason scientists call it the Doomsday Glacier. It's its position. Thwaites functions as a structural pillar, a cork in a bottle, holding back a much larger reservoir of ice sitting behind it across the West Antarctic Ice Sheet. If Thwaites alone were to fully collapse, researchers estimate global sea levels would rise by roughly 26 inches, 65 centimeters. That number alone is enough to reshape coastlines and displace millions of people worldwide. But the real nightmare scenario isn't Thwaites acting alone. Glaciologists have long warned that because of how Thwaites braces the ice sitting behind it, its collapse could destabilize the broader West Antarctic Ice Sheet, a scenario that could ultimately contribute several additional meters of sea level rise over the coming centuries. That's the reason a single glacier, however enormous, earned a nickname usually reserved for asteroid impacts and extinction-level events. Now here's what actually just happened, the development driving this fresh wave of warnings from the scientists who study this glacier for a living. Thwaites currently has one remaining natural break still in place, its eastern ice shelf, a floating extension of ice attached to the glacier's front, where it meets the ocean. An ice shelf like this doesn't stop a glacier from moving or melting, but it acts as a buttress, physically pushing back against the ice trying to flow out from behind it, slowing the glacier's overall advance toward the sea. Researchers working with the International Thwaites Glacier Collaboration, the joint American and British research effort that's been studying this glacier closely since 2018, have now confirmed that this eastern ice shelf, the last significant piece of that natural braking system, is expected to begin breaking apart as early as this year. Robert Larder, a marine geophysicist with the British Antarctic Survey who coordinates the UK side of that research collaboration, has described this remaining ice shelf as poised to disintegrate, adding that while scientists don't yet know exactly how the breakup will unfold, they're confident it's going to happen. Satellite imagery has already been capturing this process in motion. Researchers studying the shelf have observed major fissures forming right around the point where it connects to the broader glacier, with one geophysicist from the University of Innsbruck describing entire sections as suddenly falling apart into pieces based on what the imagery shows. This isn't a slow, centuries-long process happening too gradually for anyone to notice. It's an active, visibly accelerating breakup happening on a timescale of months, tracked in close to real time by satellites passing overhead. Let's be genuinely precise here, though, because this is exactly the kind of finding that tends to get flattened into pure doomsday headlines the moment it leaves a research paper. Nobody studying Thwaites is claiming the entire glacier is about to collapse this year or that sea levels are about to surge overnight. A structure this massive takes centuries to fully disintegrate, and scientists themselves acknowledge they still don't have a precise model for exactly how that longer process will unfold. What this new warning actually means is narrower, and in some ways more concerning specifically, because of how directly it connects to what happens next. The eastern ice shelf has been functioning as one of the last things slowing Thwaites down. Once it's gone, that break is gone with it, and the glacier behind it will very likely start moving toward the ocean measurably faster than it has been. To understand why losing this ice shelf matters so much, it helps to understand exactly what's been driving Thwaites' retreat in the first place, because the mechanism is more insidious than most people picture when they think about glaciers melting. Most people imagine glacial melt happening from the top down, sunlight and warm air slowly thinning ice from above, the way a chunk of ice melts in a warm room. That's happening at Thwaites too, but it's not actually the primary driver of its instability. The real danger is happening from below, at the point where the glacier's underside meets the bedrock, and the ocean, a zone scientists call the grounding line. Warmer ocean water, driven by broader shifts in southern ocean circulation, has been working its way underneath the glacier and its ice shelves, melting the ice from beneath rather than above. Research using satellite and GPS data has revealed that seawater is actually intruding more than 6 miles beneath the glacier itself, well past where anyone would expect ocean water to reach, actively accelerating the melting happening at that critical grounding zone. Because West Antarctica sits on a bedrock shelf that actually slopes downward as you move further inland, rather than upward the way most coastal landmasses do, this creates a genuinely dangerous feedback dynamic. As the grounding line retreats inland, the ice sitting there gets progressively thicker and more exposed to the ocean, which can accelerate the pace of retreat rather than naturally slowing it down the way melt on a normal, upward-sloping coastline typically would. This underwater intrusion isn't a slow, steady process either. Researchers monitoring the system have found that warm water eddies, swirling currents that can measure up to 6 miles across, are actively burrowing underneath these ice shelves, and the resulting melt can be tracked not just year to year, but literally hour by hour and day by day, using the instruments researchers have deployed directly onto and beneath the ice. Scientists have used ice-breaking research ships and an underwater robot called IceFin, purpose-built to swim beneath the glacier itself and gather direct measurements from the grounding zone to map exactly how this warm water is reaching places researchers previously couldn't directly observe at all. Robert Larder's own research team, drawing on this combination of satellite and GPS data along with direct underwater observation, has described the glacier as now set to retreat both further and faster than earlier assessments suggested, adding that the process, once it fully takes hold, may prove essentially irreversible. It's worth appreciating just how difficult and dangerous the actual fieldwork behind these findings has been, because this isn't research conducted from a comfortable lab. It's happening at one of the most physically hostile remote locations accessible to human beings anywhere on the planet. Expeditions to Thwaites require ice-breaking ships capable of forcing their way through pack ice just to reach the glacier's front, followed by teams drilling directly through hundreds of meters of ice to lower instruments, including that IceFin robot, into the ocean cavity beneath the shelf itself, an environment completely dark, near freezing, and under enormous pressure from the ice above. Researchers doing this work have described the process of drilling into the glacier and recording temperature and current data directly from beneath it as central to understanding how quickly the impact of climate change is actually reaching this remote corner of the planet, rather than relying solely on satellite observation from thousands of miles away. This direct physical measurement work is precisely why researchers can now speak with the kind of specificity they're using this year, rather than the far vaguer projections that characterized Thwaites' research a decade or more ago. So what does irreversible actually mean in this context? And why does that word matter so much more than simply saying the glacier is melting? It comes back to that same downward-sloping bedrock geometry underneath West Antarctica. Once the grounding line retreats past a certain point on that slope, the physics of the system mean the glacier's retreat can become self-sustaining, continuing to accelerate even if global temperatures were to stabilize or even modestly decline, because the underlying geometry of the ice sheet itself is now working against stability rather than for it. This is precisely the scenario climate scientists refer to when they talk about a tipping point, a threshold beyond which a system's own internal dynamics take over and drive continued change, regardless of what happens with the original external trigger. Researchers studying Thwaites have been increasingly direct, describing this glacier as sitting right at, or potentially already past, exactly that kind of threshold. Let's talk numbers, because they matter for understanding the actual timeline involved here, and it's worth being honest that this is a story that unfolds over decades, not overnight, even as the warning signs accelerate. One recent study modeling Thwaites' future ice loss projected the glacier could be shedding somewhere between 180 and 200 billion tons of ice per year by 2067, a rate of loss that would meaningfully accelerate global sea level rise well before the glacier itself fully disappears. To put a number like that in perspective, that's roughly equivalent to the entire annual water usage of a large country disappearing into the ocean as ice every single year, sustained for decades. And that's specifically the trajectory researchers are modeling with the eastern ice shelf's break still partially intact. Once that shelf finishes breaking apart, expected to begin this year, the pace of ice loss feeding into that broader trajectory is widely expected to increase. It's worth putting the scale of this threat into a wider global context, because Thwaites doesn't exist in isolation. It's one piece, albeit an unusually consequential one, of a much larger story about how the planet's major ice systems are responding to a warming ocean. Greenland's ice sheet, the other major land-based ice reservoir capable of significantly raising sea levels, has been losing mass steadily for decades, but it's driven by a somewhat different combination of surface melt and outlet glacier dynamics than what's happening at Thwaites. West Antarctica's vulnerability is specifically tied to that unusual below sea level inland sloping bedrock geometry, a configuration glaciologists sometimes describe as marine ice sheet instability, a structural vulnerability that simply doesn't exist in the same way across most of Greenland or East Antarctica. That's precisely why Thwaites, despite representing only a fraction of the world's total land ice, draws this level of dedicated, sustained international research attention, because its underlying geology makes it uniquely susceptible to exactly the kind of runaway, self-sustaining retreat scientists are now watching unfold in real time. There's a broader oceanographic story unfolding around Antarctica right now that helps explain why this warm water intrusion has been intensifying in the first place. And it's worth understanding because it connects Thwaites to a much larger pattern researchers have identified across the entire Southern Ocean. A recent scientific study examining what researchers call compound drivers of Antarctic sea ice loss found evidence of a fundamental shift in how the ocean around the continent is behaving, with heat that had previously remained trapped deep below the surface now rising upward, where it's increasingly capable of melting sea ice and, by extension, reaching further underneath ice shelves like the one currently breaking apart at Thwaites. Researchers involved in that study have been blunt in describing the pace of change as outrunning what earlier climate models had actually predicted, a pattern that's become an uncomfortably familiar refrain across Antarctic research. Over the past several years, reality consistently arriving faster than the models built to anticipate it. It's worth understanding how this glacier earned its nickname in the first place, because it wasn't dreamed up by a headline writer looking for a scary phrase. It emerged from within the scientific community itself, based on genuine concern about what this specific glacier represents structurally. Serious, sustained international research into Thwaites accelerated significantly starting in 2018, when the International Thwaites Glacier Collaboration formally launched as a joint effort between American and British polar science agencies, pooling funding, ships, aircraft, and personnel specifically, because studying a glacier this remote and this consequential was recognized as beyond what any single nation's Antarctic program could tackle alone. In the years since, that collaboration has published a steady stream of findings, each one generally pointing in the same direction, toward faster retreat, more direct evidence of warm water intrusion, and less certainty that the glacier's decline can be meaningfully slowed through anything short of substantial. Sustained reductions in global greenhouse gas emissions. This year's warning about the eastern ice shelf isn't an isolated bombshell, so much as the latest data point in that now nearly decade-long trend of escalating findings, which is precisely why researchers who've been tracking this glacier closely aren't treating it as a surprise so much as a confirmation of the direction they'd already been warning was coming. So what happens next? And what exactly are scientists watching for as this eastern ice shelf finishes breaking apart? A few specific things. First, researchers are closely tracking the mechanics of the breakup itself, since even scientists directly studying this shelf have acknowledged they don't yet know precisely how it will fracture and detach, whether through one dramatic, large-scale calving event or a more gradual disintegration into smaller pieces over successive months. That distinction matters, because it affects how quickly the glacier behind it responds once the break is actually removed. Second, scientists are watching the glacier's flow speed immediately behind where the shelf currently sits, since an acceleration in how fast that ice starts moving toward the ocean would be the clearest, most direct confirmation that the shelf's buttressing effect has genuinely been lost. Third, researchers continue monitoring that 6-mile intrusion of warm water beneath the grounding line, tracking whether it continues expanding further inland, since that advance is the single clearest indicator of how much further and faster the retreat is likely to continue. And fourth, teams are watching for any changes in the broader shear zone fracturing that's been documented across the glacier over the past 2 decades. Since new stress patterns there could signal whether instability is spreading beyond the immediate area of the collapsing ice shelf. Let's talk concretely about what a rising contribution from Thwaites actually means for coastlines, because abstract sea level numbers tend to undersell how disruptive even modest increases become once you connect them to real places people live. A 26-inch rise in global sea level, the figure associated with Thwaites' full collapse alone, doesn't simply mean water creeping a couple of feet up the beach. It fundamentally changes the baseline for storm surge, meaning coastal flooding events that used to be rare, once-in-a-generation occurrences become dramatically more frequent, turning what used to be a 100-year flood into an event that might recur every decade, or even more often in vulnerable, low-lying coastal cities. Places like Miami, New Orleans, large stretches of Bangladesh, and low-lying island nations across the Pacific are frequently cited by researchers as being among the most exposed to exactly this kind of accelerating baseline shift, because relatively small increases in mean sea level translate into dramatically larger increases in flood frequency and severity for communities already sitting just above current sea level. And that's before factoring in the much larger, longer-term contribution researchers warn could follow if Thwaites' retreat genuinely destabilizes the broader West Antarctic ice sheet behind it, a scenario that could unfold over centuries, but that becomes measurably more plausible with every milestone, like this year's ice shelf collapse. It's worth stepping back and being honest about what this means for the rest of the world, because the science here, while genuinely serious, doesn't call for panic about tomorrow. This is a story about accelerating risk over the coming decades, not an imminent flood arriving next year. Coastal planners, engineers, and climate scientists studying sea level rise increasingly treat Thwaites as one of the most important single variables in long-term coastal infrastructure planning worldwide, precisely because its behavior over the coming decades will meaningfully shape how much sea level rise coastal cities need to plan for and how quickly. The eastern ice shelf's imminent breakup doesn't rewrite that broader multi-decade timeline overnight, but it does represent exactly the kind of threshold crossing event that pushes researchers to revise their models toward faster, more urgent projections rather than slower, more conservative ones. The uncomfortable truth about Thwaites is that it earned its ominous nickname honestly, not through exaggeration, but through the genuine scale of what's actually at stake. A single glacier functioning as a structural linchpin for an ice sheet capable of reshaping coastlines worldwide if it were ever to fully destabilize. What changed this year isn't the glacier's ultimate fate. That question remains genuinely uncertain and will keep evolving as researchers gather more data. What changed is the timeline for its next major milestone, the loss of its last significant natural break, now expected within months rather than years. Scientists will keep watching, keep drilling, keep sending robots beneath the ice, because understanding exactly how Thwaites responds once that break disappears is quite possibly the single most consequential open question in climate science today, one whose answer will shape coastal planning for the rest of this century and well beyond it.